This video is looking at standing waves, and this is going to be a special case of constructive interference. So there's some conditions that have to be present in order for a standing wave pattern to occur. The first one is constant frequency, and that just means that the source that is producing the wave needs to be at a constant frequency and that you're not changing the source. So remember that we've talked about frequency only changes when the source vibration changes. The second thing is the medium, right? The medium has to be constant. So again, if we think of sound and sound traveling through air, this would mean that the temperature of the air would be at a constant state. In the case of some examples of standing waves, if you're setting up a wave, say, through a slinky, that would be a constant medium because the slinky isn't changing. Or if we're sending a standing wave through a string, that would also be an example of a constant medium because the string is the same all the way through. The last thing is there needs to be a fixed end reflection. So there has to be an attachment at the end, just like when you did your slinky lab, someone holding on to it, or the string or the spring that you are demonstrating this with is attached to a solid object. Now, to understand a standing wave, let's first draw a line that represents the axis the wave would be going down. Now, when you did your spring lab, or when you did your coil lab, when you sent down a pulse, right, you say you made a positive pulse, and you sent that down, that pulse would continue to move down, so this would be the same pulse moving down through the medium until it hit a fixed end. Then it would flip to the other side and continue down. So again, I'm just drawing the same pulse moving down to the other end, and then again it would flip over, come back on the opposite side. So we would have a single pulse going down, reflecting, out of phase, and then coming back on the opposite side. Now, we only looked at single pulses. Now, with a standing wave, what will happen is you're going to have your axis, and you're going to send down a pulse, and then this pulse is going to go down, and then immediately after that pulse, you're going to send another pulse, and another pulse, and another pulse, so you're constantly sending positive pulses all the way down. So you're not sending this one single pulse, you're going to send one, and then right after you're going to send another one, and you're going to be sending those at a constant frequency. At the same time, then they are going to continuously reflect, and they're going to reflect back out of phase. So suddenly you have positive pulses going down one side, and then you're going to have negative pulses coming back on the other. And the reason that's happening is because at this end, you are sending pulses down at a constant frequency. The pulses are going to be traveling down the medium, so this could be a string or a spring, this could be air, and that because that's a constant medium, they're going to travel the same speed all the way down, and then they're going to hit a fixed end. Again, this could be attached to a wall, it could be someone holding the end of the string, it could be attached to a post. And because there is a fixed end, then those positive pulses are going to turn into negative pulses. They're coming out of phase. And because they're out of phase, this is caused by, again, just as a reminder, Newton's third law, so an equal and opposite reaction. And then they're going to travel down the opposite side, and again they're going to hit another fixed end where the generator was, or the person that's creating the vibration, and that's going to then be sent down on the positive. So you're going to have this continuous positive pulses and a continuous negative pulses. Now, that series of positive and negative pulses going back and forth create a pattern that looks like it's standing still. And there's another video that you're going to be looking at, and I'll demonstrate one in class as well, where you're going to see a string attached to a fixed end. That is also the frequencies being created by a generator at one end. So you have the generator at one end, fixed attachment at the opposite end, and it's going to be traveling down a string. And you're going to see this pattern created, and this pattern is going to look something like this, right? So you're going to have a series of what are called nodes and antinodes. This section here is where you're going to get a series of constructive interference. And because this is a constructive interference, really what's happening is you're getting suddenly you have two positive pulses coming together, and then you get a supercrest, and then you have two troughs coming together suddenly, and then you have a super trough. So you get this constant presence of a constructive interference, or what appears to be constant constructive interference all the time. It's actually not every second it's happening so fast that you just don't never see it actually disappear. So these are called antinodes. And antinodes is where in that standing wave it looks like there's a constant constructive interference both for the trough and the crest, but really it's actually flipping from a super crest and then it flips back over to a super trough. However, again, it's happening so fast that it looks like there's both a crest and a trough happening at the same time. Now, in between those waves, you suddenly get a pattern where you're going to get no wave motion, or what you'll see no crest or trough. And this is an area of destructive interference. And this is called a node. So you get a series of antinodes, which are constructive interference. So again, that is a crest happening, and then suddenly a trough happening right after each other, and again happening so fast it looks like they're both present at the same time. And then you get a series of nodes, so really in between these crests and troughs, where you get destructive interference, where it looks like there is no wave present. And again, this is caused by having a generator at this end. So this would be a constant frequency, and then you're moving down a medium that is constant. So it could be a string or a spring, it could be air, but the idea here is that whatever it's traveling through is not changing. And then it's also hitting a fixed end. I'm just going to call it FE, a fixed end at the end. So pulses are going down, reflecting off the fixed end, coming back as troughs, out of phase, and because it's a pattern that's happening at the same rate, so at the same frequency, you suddenly get this formation of what's called a standing wave. And that standing wave, it's referred to that standing wave because it appears that it's not moving. And because it's not moving, you suddenly looks like you have a crest and a trough happening at the same time. And in between those crests and troughs, you have areas of destructive interference where it looks like there's no wave motion whatsoever. Now, you can get patterns in the standing waves, and the patterns are multiples of what are called a fundamental frequency. So your first frequency, or your first what's referred to as the natural frequency, or the lowest frequency a string or a coil can create a wave, is one antinode, so I'm just going to call them ANs. So you have one antinode, and this is a half a wavelength, because remember, a wavelength has to be a crest and a crest, or a crest to a trough to complete it. So if I started my wave count here, my wavelength count here, it would start here, and I'm going to move across the crest, and in order to complete that, I'd have to go off the screen and then finish off with the trough. So this is half a wavelength. This is one antinode. This is referred to as the fundamental frequency, or your first harmonic. So one antinode or two nodes equals half a wavelength. And this is your fundamental frequency, or your lowest natural frequency. And again, that is referred to as the first harmonic. Now, if I double the frequency, I now have an antinode here and an antinode here. And you can see that this is going to be, if I count this, I'm going to go a crest, down a trough, so again, once we finish that trough, then we have from here to here one wavelength. So we can count one wavelength as one wavelength equals two antinodes or three nodes, because we have a node at this end where the generator would be, we have a node in the middle, and now we have a node where that fixed end is going to be. So when we look at standing waves, we can start counting the number of wavelengths by looking at the pattern of antinodes. So one antinode would be half a wavelength. Two antinodes is going to be one wavelength. Or we can count two nodes is going to be half a wavelength, or three nodes is going to be a full wavelength. Now, this is twice the frequency, or 2 times f to the 0, or 2 times the fundamental frequency, and this is then the second harmonic. Now, whatever that frequency is, so if the fundamental frequency was 10 hertz, then the second harmonic is happening at 20 hertz. And so we need to take a look at that fundamental frequency, and then no frequency in between that 10 hertz, which would be the fundamental, and the 20 hertz, which would be the second harmonic. There will be no formation of a standing wave anywhere between there. So if you set something at, say, 15 hertz or 16 hertz or 17 hertz, you wouldn't get a standing wave pattern. The standing wave pattern would only occur at that second harmonic, which again is 2 times that frequency. So again, in this example, that would be fundamental 10, and then you wouldn't see another standing wave until you see 20 hertz. Now, if you go 3 times the fundamental frequency, then you're going to get another standing wave pattern. So again, in our example, if I did the fundamental frequency, then that was, say, 10 hertz. Then I did 2 times the fundamental frequency, which was 20 hertz. And then 3 times the fundamental frequency is going to be 30 hertz, just for this example. So again, you're going to get a standing wave pattern at 10 hertz. You're going to get a standing wave pattern at 20 hertz. And then you're going to get a standing wave pattern at 30 hertz. But you will get no standing wave patterns anywhere in between those frequencies. So the third fundamental frequency is going to be called your third harmonic. And again, if we look at this wave here, so we're going to start here, and we're going to end over here, then we have an antinode, antinode, antinode. So we're going to have 3 antinodes, and that's going to equal 1.5 wavelengths. So again, if I trace this, I start here. This is half a wavelength, 1 wavelength, and now we have 1.5 wavelengths. So 3 antinodes equals 1.5 wavelengths, or I could say 4 nodes equals 1.5 wavelengths, because I have 1, 2, 3, and 4 nodes. Now, for standing waves, some of the exercises that you're going to do for homework, you're going to be looking at a standing wave pattern, and one of the first things you have to establish is the number of wavelengths that are present. And you're going to determine that by the number of antinodes. So again, you would count the number of antinodes to determine the wavelength. So for example, if you ended up with one antinode, we know that that's half a wavelength. If we're looking at 2 antinodes, then we're looking at a full wavelength. If we had 3 antinodes, that's 1.5, 4 antinodes, 2, and so on. So you really, every time you add an antinode, you're adding half a wavelength. You can also count it with nodes, right? 2 nodes, half a wavelength, 3 nodes, 1 wavelength, 4 nodes, 1.5 wavelengths, and so on. So you can count using nodes, and then you can also count using antinodes. So some of the textbook work will be focusing on that, and then you will have to use that information to look at the speed using the universal wave equation of a standing wave. So again, this component is determined by measuring the number of antinodes and then using the information that's provided in the question to figure out that wavelength. So I'm just going to go through one example about that wavelength just to clarify what you're going to have to do for some of the questions for your homework. So just to provide you an example, so in the questions that you're going to do, they're going to give you a string length. And string length just means the total length of the string you're using for, or to produce the standing wave. So you can almost think of when you're using the spring coil, you would measure the length of spring coil, or you would measure the length of the string, and then from that length you're going to create a standing wave. So in the example that I've drawn here, so from this point to this point, the string length that's making this up, so from here all the way to here, is 2 meters. And so, because you need to use the universal wave equation, you need to figure this wavelength out. So that's where you're going to use your antinodes. So here we have 4 antinodes. Well, we know that 2 antinodes, so this one and this one, is going to equal 1 wavelength. So then we know 1 wavelength is going to equal 1 meter in this case. So that is then what you would use in your formula to figure out the frequency or the speed of the standing wave that you're analyzing. One tricky one that often gets confusing is they'll give you a wave with just 1 antinode. So you have to remember that just with 1 antinode, that is half a wavelength. So if they gave you, a string length of 1.5 meters, that would mean that the string from here to here is 1.5. Right? That's the length of string that you have to use your standing wave. You've produced a standing wave that only has one antinode. That would mean that because you only have half a wavelength, then your wavelength is equal to 3 meters. So that is just one area that sometimes gets a little confusing. So you're only given one or half a wavelength or one antinode. Then in that case, you have to double it in order to figure out the actual wavelength that you can use in your universal wave equation. So when you get your textbook work, again, you're going to be counting antinodes. You're going to be looking at standing wave patterns. And accompanying this video, there's another video I have posted that shows you a standing wave on a string that they will talk about the same components, just to kind of reinforce some of the concepts. And then next day in class, I will try to set up a demonstration, and we'll talk a little bit further about these standing waves and some of the applications of those waves.